Hey there, this is Mr. Herman. We're back with a video this time about the statistical testing for statistical significance in matched pairs of data. So we're looking at this one here. We're going to do a t-test in just a moment. This is the problem I gave you for homework where the Toyota Prius is a hybrid vehicle and it talks about getting gas mileage, and we're seeing if the hypermiling makes a significant difference before and after. I've covered up these because I've already pre-calculated these just to save some time. When I get to that part, you can pause the video, do your math, and then check it afterward, okay? So let's go to the first part, which is the first step. We have multiple steps here. If you look back at your paper, you'll see that there are many steps involved in this. And the first one is going to be to identify the null hypothesis, which I know most of us are ready for, so let's go ahead and do that. So it's the same every time. So we're going to put 1 and then null hypothesis, which is H sub O. For this, we're going to put the same thing we put every time. It's based on a 95% confidence level, so we're going to say that based on that, we're going to have no change. So the mean sub before is equal to the mean sub after. Remember, it's the same for every problem. So each problem you get, tests, homework, warm-ups, anything's going to always be that same thing. Number 2 is identifying the confidence level and finding alpha. So to do that, we're going to go to 95%, which we talked about is 1 minus 0.95. That gives us an amount of 0.05 for alpha. That equals alpha. And we're going to use that in just a moment. Then we go to number 3, which is identifying the degrees of freedom. Remember, the degrees of freedom are always going to be n minus 1. So in this case, we have 12 people in this sample. The average mileage is 12 things there. So n is 12, which means the degree of freedom is going to be 11. And then after that, we're going to take the degrees of freedom and the alpha amount, this 0.05, and the 11, and use our chart here, which I'm going to put down for 1 second, and we'll go back to the other part. We can use the chart, and I can use a highlighter to show how we get this. We start with the critical values on top. The alpha is 0.05, and in this case the degrees of freedom is 11. So we want to make those two match up on the chart and figure out where they match up. So we'll go down like this and over till we get to across here, which is 2.201, and then that's the value we came out with in class. So 2.201 is the critical value. So we'll say critical value of 2.201. Next step is step 4, and that's going to be make the graph and the inequality. So let's make the graph. The graph's going to look like this. It's going to be one of these normal type looking graphs. We're identifying the values that are not normal or usual anymore. So we're going to put down here and here. This is the 2.201. This is the negative 2.201. It could be either one. The first example we did in class I know was positive, but you can get a negative value also. So let's then take the inequality. It's going to look just like this. You can even put it underneath this if you want, make it easier. 2.201. Remember, these always point to the right, and then we'll interpret that in just a second. 2.201. So we're saying that our t-value has to be in this shaded area here for it to be considered something that works, or that's usual. In other words, to reject H sub O, which is this here, we have to have a t-value inside these regions here, not in the range of normal values. Then we're going to go to 5, and on 5, we're going to move this up just a little bit for this. 5, we're going to start doing some math. So this is the part where I got these all calculated already, so if you want to go ahead and pause this for a second, pause it, and then I'll pull those off, and you can start calculating your totals. So on mine, for the difference of x, which is subtracting this minus that, I got negative 5.6. And again, subtracting here, I get this. And this one here, you get this whole one by subtracting. These are the differences. Then we square them to get all positive amounts. Remember, if you square these, you get positive amounts. Put in the calculator with parentheses. And then after that, you would go through the process of bringing these down and find their sums. So the sums for each of these, the sum of x, in this case is negative 35.5. I think one of the classes got this far. And the sum of x squared is going to be 7 759.41. So those are the values we got for that. Now we're going to use that to calculate standard deviation. So the standard deviation is going to be, again, the formula for that's on the previous page. We're going to substitute these values in for that. So it's going to be the larger amount. So square root of, parenthesis, extra parenthesis, remember you need 2 there, 759.41 minus, I'm going to put that in parentheses, negative 35.5 squared. Make sure you're careful, it's a negative amount. You've got to put in parentheses for this to work. And then divided by, we have 12 values, right? So we're going to divide by 12. And then parentheses, divide by 11. And our standard deviation is approximately, when we do this, we get approximately 7.71. We said to round to the nearest hundredth, and that's what that is. Then from here now, the next step is to calculate t. So t is going to be taking the differences of the x sub mean differences. Let's write this out again so you can see this to make sure we're on the same page. Divided by the square root of n. So I'll put this into a calculator in parts. This part first, then divide by these two. So the mean of the differences is going to be taking this value right here, that's the average, right, the differences, and dividing it by 12. That's going to give us this right here. It's the average of the differences, these here. So take and divide those two, and you get negative 2.96. Actually, we need to put this there, divided by. Let's start with our parentheses with the calculator. You'll need 1 here. 7.71 was the standard deviation. Divided by square root symbol, and there was 12. And I think you only need 1 at the end. We determined in class like this. You don't need to put 2. I think if you put 2, it works also, though. So check and see. I think only 1 is necessary. That gives us approximately negative 1.33. So now let's interpret this. Let's take this up here and take a look here and see what we got. We got negative 1.33. Let's put that on our graph. Within an approximate range, not exact, it would come somewhere in this area here, negative 1.33, which means it did not fall outside the usual values. It was in the range of usual values, which is 95% of normal values. So now let's break this down into parts here. Our explanation has to be in 3 parts. First of all, we have to say whether it was in the interval or not. And in this case, it was in the interval of usual values. Okay? Then we're going to say, do you reject or fail to reject it? In this case, we're going to, well, we'll talk about that in a second. And then after that, we say, did it work or not? So let's start with the sentence for the last part. For the conclusion, you need to say, T fell into the usual range of values. And then we say after that, comma, therefore, now are we going to reject H sub O? Remember, rejecting this means that there was no change. Or we could accept it. I'm sorry, not accept it, but fail to reject it, which is the same as accepting it. So we're going to reject this because, we cannot reject it because really there was not a no change. There was no change. Inside here, it stayed in here, so we're going to fail to reject it. So therefore, we fail to reject H sub O. And then your final statement just says whether it worked or not. So we're going to say hypermiling doesn't work. And that's our normal statement that comes out of what we're talking about. Is for normal people to understand. At the end of the study, you're going to want to put it in normal terms, and that is, it doesn't work because it did not go outside the range of usual values.